To complete the lecture or sort of the topic of principal component analysis and KL transform and others, let me show you some example of what we're talking about. I think we can start with something here. So I take here a faces data set, Olivetti faces, and we can think about vector representation if we just plot, say, it's this one is the cars data set, I think. Yeah, car crashes data set. So the numbers are here are for the individual cars, and the uh, numerical values are for features. So speed, alcohol, not distracted, and blah blah others are just feature values. So that's your vector space. We can make this variable categorical, and all of those variables will live in their corresponding subspaces. That's one example. Then, of course, we can look at correlations between subspaces, between different features by plotting their scatter plots like that. But I will make the code available, and you can look it up. What exactly am I doing there? But that's not that interesting. Let's think about like higher dimensional spaces. Here, each feature had a name. We knew what we measured, but let's look at 4096 dimensional space of human faces. Each face is represented as a 2D image, and let's look at two specific images in that space. This is a 4096 dimensional space, dimensional point, or rather a point in 4096 dimensional space. And this is another point randomly picked in that same space. Well, the only difference from a real space here is that we can say, well, gray values in each pixel are within some reasonable region, or we could also say to relaxing that to outside of the cube, or to some kind of a continuous space, we can say that the gray values are likely to be in some region. Some point could be super high, some point could be super low, but anyways, where in this 4096 dimensional space do human faces live? Well, let's take those two and let's just walk on a line from one point to another. All I'm doing is just literally walking on a line in this 4096 dimensional space along a line and plotting what I see, like all of the points with some interval. You can say, hey, but that's just simple linear interpolation. But what is linear interpolation if it's not walk along a line in the multidimensional space? That's all we're doing. That's linear interpolation. Let's take two actual faces, because the space could be vast, and this point could be super far away from this face or any of the faces in this dimensional 4000 dimensional space. But the faces themselves may be clustered close together. Although we will talk about in our next lecture in course of dimensionality about how compact are spaces of large dimension. Let's walk on a line in the faces space from one face to another. And interestingly, while we're doing that walk, none of images or none of points look like random noise like that. So if we take 2 points which represent faces in that multi-dimensional space and walk along the line between those 2 points, everything on that line also looks like a face. And then we kind of morphing one face into another, but all we're doing here is just a linear interpolation. we can also illustrate transpose operation. It's a continuous linear algebra refresher. So I put this square on the face and I transpose the face and look, it's not a rotation because if it was a rotation, the square would have been here. But that's just an illustration of the transpose operation. But now look at the matrix inverse, another matrix operation. Notice the following, that those are two spaces that are dual of each other. And the space of inverse is sparse, while the space of the face is dense. And when the space of inverse is dense, actually, the reverse will hold. It's similar stuff in other spectral decomposition and other bases when the spaces are dual of each other. We have talked about how sparse an independent representation of a Gaussian becomes when we transpose it into the, or transform it into the space of its eigenvectors. So now, okay, ignore this failed experiment. Let's look at the following. Let's take our matrix and our data matrix of all of the faces. And although I'm doing SVD here, all I'm interested in is in finding eigenvectors of the covariance matrix. So I could first have computed eigenvalues and eigenvectors of the covariance matrix. I could first have computed covariance of X, and then I'm plotting the eigenvalues. And what I'm seeing, I'm assuming all of my phases are sampled from Gaussian distribution for now, just for a second, so you know. And I'm seeing my principal axis of the ellipsoid, of this Gaussian ellipsoid, have importance that widely varied. Like this is the highest eigenvalue, this is the lowest eigenvalue. Looks like most action happens up to here, up to first 10, maybe 20. The eigenvalues or eigenvectors, principal axis. That's what I of the ellipsoid. That's what I was looking for. And if I look at corresponding eigenvectors, I see this is an eigenvector. I take an eigenvector, which is a point in space, right? It points somewhere, and I plot it here. And those eigenvectors, especially when we plot with faces, when play with faces, for fun, are called eigenfaces. So that is a representative or principal axis of the face space. Let's plot first 16 eigenfaces that correspond to the highest eigenvalues. So this is our highest eigenvalue face, and then we're getting various faces by, remember our spectral decomposition, nothing but a weighted sum. By carefully representing each phase as a weighted sum, that's what KL transform does basically. We represent each phase as a weighted sum of those eigenvectors, of those eigenfaces. We can reconstruct any possible phase. But another point of PCA and the exercise is, okay, let's go back here, is the fact that those lower eigenvalues, the eigenfaces that correspond to those lower eigenvalues, may be not as important for our task and for recognition. If you think in Fourier analysis term, the eigenvalues on the tail end correspond to higher frequency components, so very finer detail of the faces, while those eigenvectors and those eigenvectors that correspond to those eigenvalues or eigenfaces that correspond to the larger eigenvalues, they encode the bulk features of the face. So let's make sure and let's look at that. Let's take, yeah, I will need to pause the video and rerun this notebook so we can play with it. Just a second. Okay, let's look at these two random faces. No, I don't like. They kind of all too similar. let's see. Ignore, don't pay attention to what I'm doing yet. I will explain. I just need to find a set of faces that are not the same, or this is even not the same person. Okay, sort of different. Uh, uh, no, let's try to find randomly. I'm just randomly selecting a pair of faces from the data set to demonstrate the point. Well, okay, this guy has glasses and a beard. Let's look at this two faces. So what we're doing now is let's take only the first top two eigenfaces and reconstruct these faces that you just saw was using just top two eigenfaces and their corresponding weight values. But we're trying to reconstruct this 4096 numbers with just two numbers. Okay, with two numbers, the compression is too severe. There are some differences, but they're still very, very unlike those people. So let's try 10. Just radically increase 5 times. So each face, oh, look, now with just 10 numbers, we can compress using PCA with just 10 numbers. The faces already look different and maybe similar, recognizable, but let's put it to 20 numbers, 20 eigenvectors, or 20 principal components. Okay, something better. Let's jump to 50. Okay, 50 is already pretty good, pretty close. So 4096 pixels can be reasonably represented with 50 pixels, but of course the quality is not as good as JPEG compression of the same images. But we're not doing JPEG compression. We're just doing linear algebra, and 150 were already super recognizable. Tons of high frequency features are missing. There seem to be like a halo, an artifact of glasses for this guy, but still, look how good it is with just 150 numbers. That's actually how compression, even JPEG compression works, but basis functions or eigenfaces are different. So each of us can have the eigenfaces stored on our hard drive, and we can just send around the coefficients to each other and reconstruct those faces. That's one example of compression, how PCA can be used. But mostly we assume that higher frequency, so 4000, right? Let's just take 1500. There is no, well, because we didn't have enough faces for that. The number of examples, the number, well, maybe there were 500 faces. No, 400 is the max. Okay. Because the number of faces in the data set is low, we cannot use large number of eigenvalues, but okay. With just 300 numbers, we can reconstruct the faces almost perfectly, and with 200 numbers, just for example. It's a very good, reasonable quality. The same we can do, another example here, with the same we can do with MNIST handwritten digits. So I'm interpolating or just walking along a line in the MNIST space, and I think it's 700 plus dimensional space. I'm making this code available to you as well, showing the same results. The eigenvalues for MNIST look quite different. This is log space and this is real space. Well, this is log on X, but by 100 well, even by less than 100, by 50, we have everything that we need for MNIST handwritten digits, and those are principal components or eigen numbers now, not the eigenfaces, but eigenfaces of MNIST. So if we draw a random sample of MNIST, and then those are eigendigits. Nice, right? Um, so you can read about this. I wrote some comments for you. So same exercise of trying to reconstruct a number with just 30 top components. And well, just a little off topic about, yes, so if we take PCA and if we take principal components, two principal components or two eigenvectors that correspond to the largest eigenvalues and make them an x and y, like we can display the full 700 dimensional space. Let's just choose the principal components of this matrix and plot all of our data here. Each point is an MNIST digit, and I colored those digits, those points, in correspondence with the digits that they represent. And as you see, the ones are sort of clustered together. If we look in this projection, in the PCA projection, just a two-dimensional cut in the 700 dimensional space. But the rest doesn't make sense. So there are other methods that we're going to cover in the manifold learning that can represent this whole 700 dimensional space in 2D, such that, and this is not supervised learning, this is just projection of the data into 2D, but it's a nonlinear projection, such that all those digits cluster uh, together. Because in that 700 dimensional space, as you saw with spaces, they all kind of live nearby, and by linear interpolation, by the neighborhood in that linear space, you can see the actual semantics of your data. Okay, that's enough for the demonstration.